All right, welcome back to calculus. So we're going to look at volume. We're mainly going to look at the idea of trying to find volume using a axis of rotation, where we're going to have a particular equation or set of equations that are going to create a region for us. We're going to rotate that region around an axis, horizontal or vertical, and then we're going to use washer method to find the volume of that object, that solid that is created by that rotation. In another video, we'll also look at how to do this if it's not a rotation, if it's a constant or a consistent just cross section, but not necessarily a rotation. So let's just start by getting some equations down here, or some shapes of some sort. So let's just say that we're dealing with, I don't know, let's have our y equal to, say, x squared plus 1. And we're only going to be looking where x is greater than or equal to 0 here, okay? And what we're wanting to do here is we're wanting to be contained. What we're writing out here are our constraints. Okay, so we're saying that the region we're rotating is going to be contained within these constraints that we're writing out. And then let's say that we have the line, say y equal to, say 2. And then we want to rotate about or around y equals, say, 4. Okay, now let's not do 4. Let's do 5, because that's gonna make the numbers pop a little better with what all the pieces are. All right, so let's just get an idea of what this shape looks like. So the parabola with x squared plus 1 starts at y equal to 1 and then goes up like that. Okay, and we're probably not going to use all of that because we remember these are our constraints here, so we want the region completely contained inside that. And then our second constraint is y equal to 2, which is going to look more or less like this. So here's y equal to 2, and this was my equation right here of y equal to x squared plus 1. Right? And we could also use f of x, g of x, and things like that to make this a little bit easier. And then, of course, x is greater than or equal to 0. So we're talking about rotating this space right here, this region, around the line y equals to 5. So I'm just going to create a little dotted line here, and y equals 5. Okay, so that is our axis of rotation. Now, a couple things that we first want to deal with, and this is how I go about solving a volume question anytime that I need to deal with one of these. I always know that it's going to end up being, since we're dealing with the rotation, my cross sections, meaning there's that space up here above that would be on the top of this. So we're looking at something that looks kind of like a bowl on the outside and then a cylinder on the inside, because you're going to have this shape. So I don't know if I can draw that very well, but it's going to kind of look like this on the outside. You kind of have that curve, right? But then it has, and this is where my drawing is going to be really, really rough. You're going to have kind of like this cylinder-looking piece in the middle of this, all right? That's going to be kind of a cutout in there. So you have the cylinder in the middle. Use your imagination a little bit here. Maybe grab some Play-Doh or some kinetic sand, and we can cut these out and build this shape. But it kind of looks like a bowl, and then you have this cylinder cut out of it, out of the piece of it. So maybe like a convex lens, but we've bored out a piece out of the middle of there. All right, so that's that shape, what that looks like. But when we do a cross section, when we cut across this thing, we're going to cut across from the axis rotation over this way. What is that slice going to look like? If we were to turn this into a loaf of bread and we were to cut out that slice, so I'm going to take it out of there and lay it down on the ground, it's going to look like this, more or less. Imagine it, pretend it's symmetrical, right? Okay, so we have this outside radius, right? And we have this, oops, not that far. Then we have this inside radius right here, which I can't even draw, that little inside radius right there, which would just be a little r. So we have this outside radius that goes from the axis rotation to the outside edge of our figure, which we'll call big R. And then we have our inside radius, which goes from here to here, and that'd be little r. That'd be that distance right there. Okay, so those are those pieces. Now the rest of the equation we want to deal with here, since I know, and I kind of paused over here writing the equation, but I know since I'm doing that cross section is circular, I know I'm doing pi r squared, right? And I know I'm doing a big circle and I'm having to take out the little circle, so I'm doing the subtraction of those two circles, right? So I'm taking the big circle and subtracting out the little circle inside of it, the area of those two pieces. And the pi is multiplied by all that in order for it to be the area of those circles. So pi r squared minus pi r squared. And since they both have pi, we can just take the pi out, factor it out. And it saves us a little bit of multiplication in the long run here. Okay, a little bit of work here. But we have d something. What's the something here? Is it dy or dx? We had a 50-50 shot here if we just want to guess. But let's think about how we're stacking these pieces. The first piece, that first slice that we'd make, would be right here at y at x equal to 0 along the y-axis, and then make another slice. You can think about if we were stacking CDs, or if there's a loaf of bread, what direction would we stack the bread? Would we stack the bread along the counter, or would we be stacking the bread on top, and the bread slices on top of each other and building a tower out of it? Which would we be doing? Well, in this case, we'd actually be stacking along the counter here, which is a horizontal axis, which means that what's changing as we go along the counter is the values of x. So what's changing are the x values, which means that we need to count this in terms of x's. X going from right here at the x-axis, which is easy, that's 0, and then going all the way to right here. Well, we're going to have to do a little bit of algebra to figure that piece out. So what we got is x squared plus 1 equals 2. Okay, now you're like, where'd you get those two pieces? Well, this is the first equation, that's the second equation right there. Up here at the top, I got my two equations that are defining that point of intersection there, and that's what I need to do. So now I can subtract. Since I have no middle term here, I could use the quadratic formula, and maybe I can go back and do an entire example of just how to use the quadratic formula to find those values if you want. But we have no middle term, so we can do this way, subtract 1 from both sides. So 2 minus 1 would give us 1, so x would be equal to plus or minus 1, because the square root of 1 is 1, but we're starting off with squared, so we'd have the plus or the minus. Now, all my x values up here, remember the third constraint that we talked about was x has to be greater than or equal to 0, so I don't even care about the negative one there, I just want to use the positive. So now I know that intersection occurs at 1. So we're going from 0 to 1. Now we need to fill in these pieces here. So let's go back and talk about these values of r. So we got big R and little r. So let's first talk about big R. What's defining this distance of big R? And this is one of them that's a little messy to deal with from time to time. This distance right here would actually be, say, y1 if we want to give it some type of name. Okay, so there's my y1 value. So there's r1. Now, that's not r though, is it? Now, hang on. Let's think this through for a second. If we go up here, this line right here, this is y equals 5. That whole distance from there down to the x-axis is a distance of 5. The curve, the outside curve here of my figure is going to be defined by x squared plus 1, right? Or the y coordinate right there, yeah? So this distance, this distance of r, that red piece there, that is 5 minus this y value. So it's 5 minus y. In this case, it's actually y1. Now, the thing is that we're counting in terms of x's, so we can't leave this as y1. So this means that big R is 5 minus another definition for y1 would be x squared plus 1, right? And I can rewrite that as 4 minus x squared. So now I have the first piece, 4 minus x squared. Now we just need to figure out little r, right? Well, little r, if we talk about this being y2 here, the whole distance from the axis of rotation down to the y-axis is a distance of 5, but we want to that inside edge right there, which is actually a constant value of 2. So here, little r is 5 minus y2, and in this particular instance, y2 is just 2. So that's 5 minus 2, so that means that little r is 3. So you got 3 right there, okay? And then from there, it's just a matter of multiplying everything out and doing your integration, which is a pretty straightforward process there. You use your first fundamental theorem of calculus to evaluate all that stuff, and you're set. And I think the problem most students have is, when they run into this, is how to first pick whether I'm doing dy or dx, and then how do I set up my equations and my bounds and all that stuff. So let me just quickly recap that, and of course I encourage you to pause, rewind as needed through the videos. But the idea here is that we needed to first figure out how are we stacking these pieces. So getting that drawing done first is paramount, right? We have to get that done first and correctly in order to be able to understand what we're looking at, literally, right? So then we start making these cuts along the axis, because our cuts are going to be perpendicular to our axis of rotation. Now, in some texts, you'll run into these rules saying, when you do this, you do this. I'm asking you to think this through a little better, because I think this will stick better in your mind if you think this through. My axis of rotation is horizontal. My cuts are perpendicular to my axis of rotation. So my cuts are vertical cuts. Well, if I'm making vertical cuts, how do I stack vertical cuts? I stack vertical cuts horizontally, right? I'm stacking those cuts along my axis of rotation. So my axis of rotation is going to dictate what direction I'm stacking things. I'm stacking things horizontally because my axis of rotation is horizontal, which means I need to count in terms of x. So that's why we have dx here. I'm counting in terms of x because I'm counting horizontally. All right, so 0 to 1 is defined because I'm going from x equal to 0 to x equal to 1 because I'm counting in terms of x's. Now that I have this dx defined as being my variable, then I need both of my r's, or if I'm just using a disk, because I don't have a gap or a hole inside the figure, then I would just need the first one right here. I wouldn't need the little r. So then I just need to make sure my expressions here are in terms of x. So you can always write them in what makes sense. In this case, I did 5 minus that y1. But I knew I had to rewrite this in terms of x's, so I had to replace y1 with what was actually defining that shape. And then I was set from there. All right, so I hope this is useful. Hope this is helpful. If you have additional questions, please reach out and ask as you need. Take care.